What's going on, everybody? Thanks for joining the show today. Today, we are talking about something you may not realize exists, and that's the great AI traffic jam. Here's what we're talking about. We talk on the show quite a bit about what LLMs can do. We've watched as prices have come down on the LLMs and the ability of what AI can do. But here's a really big problem that probably not enough people know about. Now, the big players we're going to talk about, they definitely know about this and they're definitely moving towards it. But we've got a traffic jam problem. And one of the things that we looked at, if we just look at some of the numbers, and I did some Google Deep research on this. So take this into consideration, right? As we're getting our GPUs and our CPUs are getting smarter and smarter, obviously we have this insatiable paradox of AI paradox where our hunger for energy is skyrocketing. So much so that, to say, put it in perspective, by 2030, they're predicting the global data center electricity consumption could reach 945 terawatt hours. Now, if you're like me, you're like, yeah, okay, great, 945 terawatt hours. Like, give me some reference point to that, because I wouldn't know what that was either. But that's an equivalent to the current annual electricity demand of the entire nation of Japan. So we're talking about just global data centers, not what the rest of the world needs. And that's a prediction for 2030. So what are we talking about here? So it's not really just an energy problem. It's actually like a fundamental performance crisis. And so we have some big players that we're going to talk about: Nvidia, Intel, AMD, TWMC, others that are in play that are new startups, about how we fix this giant, very, very important data AI traffic jam. So this is the Daily AI Show. Today is September 30th, 2025. I'm joined by Beth and Andy. And guys, let's just dive into this. I'm going to give you the exact analogy that Google Deep Research gave me. And can I just pause here really quick, as I did, and I trapped my wife in the kitchen just a little bit ago, because she's home and sometimes she doesn't get away from me when I'm talking about AI. Can we just say again that Google Deep Research, in my opinion, is second to none when it comes to putting together really, really good research or thesis or plans of action? I am beyond blown away over and over and over again. In fact, today I'll even share some infographics and a webpage that it created for me after it did all the research. But it gave me, first and foremost, a really nice analogy for explaining it. So I'm gonna lay this out first, and then we can dive into the conversation, guys.
Just in line with that, were you using aistudio.google.com?
No, I'm using it inside of Gemini, scaled through our team account. I'm able to get Gemini 2.5 Pro and Deep Research in there.
Okay, got it.
Yeah, so I do believe you have to have the paid side of Gemini. I'm not suggesting this is free, although through AI Studio it could be, because a lot of what's in AI Studio is free. So yeah, if you're not using Deep Research or you have it and you have an ability to do free, Andy will check. Highly, highly recommend it. Like today, do it today. It's that good. I think everybody should at least see what it can do. Use any topic on it. I think you're going to be blown away. Okay, let's talk about our city. So I'm going to read you just a little bit of what it says. Let me get to where it is. Well, I missed it here. See, I had it on my screen and I scrolled and it's fine. All right, I'm gonna wing this because I kind of get the idea of it, right? We know we have Moore's law, and Moore's law was basically saying that every 2 years we could double the amount of transistors on a microchip. And that's not something that people are necessarily found. Justin Huang from Nvidia said Moore's law is dead. There's a lot of like evidence to that fact, but this is what we were building on forever. So imagine this city, and it's a data center. The data center is the city, your metropolis. And we've gotten really good at making GPUs and CPUs even more, even stronger, right? Even more impressive on computations they can build. And we built up these skyscrapers in the city. But the streets are made of copper and the cars are made of electrons. And this is one of two parts of a fundamental problem, our traffic jam problem. Copper and electrons moving across it is slow. It produces heat through friction, and it can only move so much across it. And what you end up having in this big city is, number one, it's estimated that 75% of the data is just in moving things around, not computations, just the actual act, the physical act of moving stuff around this city. Mind you, this is all happening on a microchip. This is all happening on a small chip, right? You know, when Nvidia, Jensen Huang holds up one of these things you can hold in your hand, that's what we're talking about. But in our mind, it's this big city. So we have this old infrastructure. We built these streets out of copper. We built our cars out of electrons, and it's causing problems. Second problem we have, we'll jump into both how they're looking, the big players are looking to solve this through verified technology. And then there's even some things this can go on to the future. The second problem is how the actual city is built. Imagine, if you will, that we build the most efficient airport with the most efficient supersonic airplanes. But in an error of ways, we decide to build this supersonic airport 50 miles outside the city center. You still have to use the old inefficient cars and copper roads to get to it. So no matter how fast it is, you still have to use the slow way of getting there, which still causes the same logjam, even though we can get to it. The way they outline current microchips and the infrastructure is that these are typically this use of what we're going to talk about, photons, and converting things into light is happening on the fringes of the chip. So now instead, think about a new process where we move that super efficient airport dead center in the middle of the city where everything else is happening. Now, what this changes actually on the chip is the difference between moving something inches to millimeters. And when you do that, you obviously increase boatloads of efficiency. So that's one problem, is we have companies that are fundamentally looking at rebuilding the chip. Our old infrastructure doesn't work. But wait, hold on. What about those roads? What about those copper roads and those electron cars? Well, we need to replace those too. And what we're replacing those with is silicon and light, photons. And when you do that, you get orders of magnitude efficiencies. You get reduced heat. You get reduced or you get increased speed. You get reduced resistance, and you also get reduced distances that things have to travel, because now they're traveling at the speed of light. Now, mind you, right now we're building towards a future where we move. So the communication, okay, it's going to be happening with photons, and that in itself will be a huge improvement. In the future, because of quantum computing and things like that, eventually the Holy Grail would also be doing the calculations. What happens when we start doing the math with light as well? And so you can see there's like sort of a process here. We have old, outdated infrastructure cities that we need to rebuild, fundamentally rebuild, new ideas, new technology. We're getting away from copper and electrons. Well, electrons are still going to be used for computation. We're there still, but we're going to be moving things around with the speed or near speed of light, right? Around the chip. We're rebuilding the city as a high level. And then eventually the Holy Grail would be that also computations are done by light. So when you look at where AI is today, why does this matter? Well, we have a logjam. We actually have the potential, if we don't fix this, of moving into sort of a dark age, meaning that despite the fact that we might have all the abilities of LLMs and AI to do amazing things, when it comes down to it, we can throw everything we have with GPUs and CPUs and all the data and all the energy we can amass to try to fix complex things like AlphaFold is doing with three-dimensional proteins and solving the next cancer and all the things that go along with that, or global warming. That would be another one that's just fundamentally hard. Think about building an actual digital twin of the Earth. That happens. That's a thing. But it's so fundamentally expensive in energy and heat and everything else that it doesn't quite make sense. But once you start able to move things around by light, photons, and not by copper and electrons, and using silicon for the roads, things change pretty drastically. So we're looking at a future here in the next several years where right now it's 75% of all the energy required is just going to moving things around. And we're going to drop that down to a very, very low percentage of the total, which means that the energy we are spending is going to computation. And that's where we want to be putting the energy and speed. So I'll stop there. I just thought that was like so helpful for me to visualize this city, to visualize ripping out the roads and rebuilding them with silicon, figuring out how to move things around, high-speed rail versus old, cars, and stuff like that. And then obviously rebuilding the city to work better for the ways that we want to move this information around. What do you guys think? Does that kind of line up with what you were thinking coming into the show today?
Yeah, it does. Let me put some analogy to the energy requirement for what we do with AI, and you've probably heard these things before, but an LLM is not terribly energy inefficient compared to the other models like diffusion models that have to generate an image or a video. So, but the fact is, like, there's a lot of simple queries in text that are happening in LLMs, and they're not terribly, consumptive, let's say, of either energy or the evaporative water cooling that's necessary to generate that result. So here's a comparison between a simple text query and a 5-second video generation. So in microwave equivalent time, right, a simple query is like turning on your microwave for 1 second. A 5-second video clip is turning it on for 1 hour. Okay, it's a huge difference. Now, when Nano Banana came out, everybody was out there playing with the, image generation, and just doing a simple image generation is only like 20 seconds. But when you make it do a video, which is a bunch of frames of images, right? That's where it's really, really energy intensive. And then you have on this the energy requirement to actually cool those processes. So that's just the electricity that's used to generate those results. Then you've got the heat dissipation that's required. And right now, what's happening is a lot of that is being done in areas like Arizona, where there are data centers, right, where it's really hot in the summer, and that makes it really expensive. It uses an enormous amount of water. To give you an idea about that, it takes, now this is not just the amount of water running through the coolant closed loop system, because they're not closed loop systems today. They're using evaporative cooling, big fans outside that are evaporating water to cool off the other closed loop, refrigerants that are being used to cool the systems. But eventually they're going to figure out how to do a closed loop system that doesn't actually evaporate the water back into the air, because the process of that evaporation requires additional energy that's not even included in that cost for the compute side. So it's really, really inefficient now. And that's where I think I wanted to just add to your main thesis, Brian, which is that we have a pretty inefficient layout at the moment for all of our compute. And also because that's running a lot of electronic data through copper wires that have resistance and generate heat, there's a lot of interest in moving to photonic transport of that data, because that doesn't generate heat in the process. Like, those photons can fly through there zillions of times, and it won't actually generate that heat.
Exactly. And part of what is so key in this, and what I find so interesting, is that while these changes are in the sort of nascent stages, like the research has been done, there's proof of concept, there's those kinds of things, but they haven't been fully put into manufacturing, although it's expected to be part of manufacturing in 2026. If we look, but like not it's not a sea change in manufacturing in 2026, but for one chip, it will move from the like prototype stage to actually some production, is in the context of us also having the conversation about all of the big power moves that people are putting into place, right? So we're going to bring online a gigawatt of energy production, right? We can do that in the we can like all of the big companies are making deals with power sources so that they can bring on more data centers. And those are long-term deals, right? Like I can, Google can make the deal right now, but that doesn't bring the power online. This actually, in a reduction of the consumption of power and heat production, could happen in a much faster way, right? Like much faster than you can build another nuclear power plant, right?
Right.
Like we can greatly lower what is the energy that's required.
Yeah, I 100% agree. Like, I mean, this is probably not super relevant anymore, but I had always heard that it takes about a decade to build a new nuclear reactor, perhaps more than that. Now, I think there's been a lot of improvement there. That might be a little outdated. Growing up, that's always the way I sort of understood it. Obviously, there's been a lot of improvement, and not necessarily the point of today's show, but we've talked a lot about like these micro nuclear reactors that literally sit on site at the data centers and produce, hopefully unlimited energy. And so there's, to your point, Beth, like there's a lot of progress there. And by the way, that's happening concurrently, right? That's not stopping. So
Right.
what's great here is that we are actively looking to solve the energy problem, which, I mean, nobody's going to be mad about that, right? If we're able to solve that. Obviously, there's some really big holy grails in nuclear. But also what we're looking at is just simply making what we do have move much and work much, much, much more efficiently. And I think that's what's really exciting to me, is that we're looking at the problem, and I say we collectively, but you know what I mean, about like the main players here are looking at the problem and fundamentally thinking about how we rebuild. To me, it would be analogous to thinking about the city of Venice and when the square floods, which has been happening forever and ever and ever. And the waiters have the waiters of the boots on, and they're walking across. They put up stanchions and chairs, and they've sort of figured their way through. And of course, it's accelerating because of sea level changes and things like that. But trying to fix the problem we have right now, to me, is analogous to what we've been doing in the past, is coming up with new ways to deal with the problems on the chip. So there's been new infrastructure literally put on the chip that deals with heat dissipation, that deals with whatever, which, by the way, also causes more, energy to be used. But these are stopgaps right now. This is putting the stanchions up and saying, here's a way to walk over the water. The water's still rising, but we'll give you a way to walk over the water. It's a stopgap. Now, Venice also, I think it's sort of famously failed so far, but they also built this multi-billion-dollar, it helps with tides, and it like the whole thing blows up with air and comes up and sort of stops incoming water during tides and things like that. And I think they basically built it. The last I saw, they built it. Basically, it's already irrelevant because it was built for 10 years ago numbers, right? And so water is still coming over the top of it. And so Venice, of many cities, but I would put Miami in there too, honestly. Downtown Tampa, there's areas down there that are famously low-lying and flood all the time. But Miami's having this issue all the time, where you see more and more videos of people walking through water, right? And so you go, okay, well, we're fixing ways to do that. We're damming here, we're diking over here, but it's causing more infrastructure. It's causing more energy to do all those things to work around the problem. This is like saying, hold on, stop. Yes, that has to happen for now, but here's our new plan for Miami, right? Here's our new plan of how we're going to basically eliminate this issue going forward, and whether that's energy or otherwise. So to me, it's obviously very, very exciting. And I think what we could do here is, I'm going to share this on my screen just as some visuals, also just to show, some of the things that Google Deep Research will do for you, or Gemini in this case, I guess.
While
But
you're
then
bringing
let's
that up, I'll just
Yeah.
say I looked into Google Deep
Oh, great.
Research, and on AI Studio, there's not a manual toggle to add deep research, but
Okay.
in Gemini.google.com, you can use deep research, but only with Gemini 2.5 Flash. If you want to use Gemini 2.5 Pro with deep research, which is a better combination, but 2.5 Flash is probably going to do the research part of it pretty well. You'll have to have the upgraded subscription.
Okay. And that's what I have, right? I have the 2.5 Pro up here. So just so people know how I did this or how I got Gemini to do this. But I thought this was a good, this is the website, and I'll show you the infographic as well. Now, it wasn't perfect. I'll show you exactly where it kind of messed up, and I asked it for, you can even see it here on the side. The player section is missing Nvidia. It told me to fix it twice, and it didn't. So I'm not here to say it's foolproof, but we have a tale of two data cities, as we were talking about, and just a really basic graphic of like, this is the copper city today, and it even colored it copper, and we're moving, you know, our little electron cars are moving to and from. And then this is its little visualization of now using light, and just a simple visualization of just what we're talking about, you know, if nothing else. And so it gives us two examples here. So the crosstown latency is really high on the copper. The grid power draw is very high, and the airport access speed is really slow. But under this new idea, then the crosstown latency is ultra low, grid power is low, and the airport access speed is instant. And when we're looking at this solution, you can kind of see where we are today, which is this pluggable optics. We're going to move towards co-package optics, which is the term for this. And then future would be photonic compute, which I told you was the holy grail, right? So if we look here, pluggable optics today, this is the current standard. Electrical signals travel across the main board to a pluggable module at the edge of the server rack, which then converts the signal to light. It works, but the electrical distance wastes significant power and limits bandwidth. So this isn't the car problem. This is the distance problem, right? Going to the edge. So then if we move on to co-packaged optics, the optical engine is moved from the edge of the board and placed inside the same package as the GPU. This shrinks the electrical distance to millimeters, drastically cutting power consumption and latency, enabling much higher bandwidth density. And then the future, photonic compute. Now, this is something that's future, right? This isn't something we're doing or even building at this point. That would be the co-package optics. But the photonic compute is the ultimate goal, using light itself for computation, not just communication. This involves creating photonic circuits that perform mathematical operations like matrix multiplications. It is a massive research challenge, but promises unprecedented speed and efficiency. So when you think about this photonic compute, this future state, and you think about our progresses being made towards gaining more energy, nuclear, right? Things like that, you can see that these are just two of many ways that we are trying to fix the problem, which is AI, as smart as it will be, built on outdated cities and having to move around outdated cities, and also having to continue to not use like light itself for computation, is going to be a limiting factor. And it's just going to mean that either A, we would have to just continue to build more and higher skyscrapers and say it is what it is, and come up with new novel ways to help offset the heat, dissipate the heat, as Andy was talking about, or figure out new novel ways to get those little electrons to move around the copper a little faster. But this is probably the way to do it. And so here's where I was just going to show you really quick where it did not bring in the other ones, because it's not just AMD, it's Nvidia, AMD, Intel. What is it? TWMC? I always get it backwards. TMWC. TWMC.
TSMC.
TSMC. Thank you. The TSMC is not like they're involved a different way. So that doesn't really show you here, but I'll just show you the rest really quick. So it has this little like switch to optical, and we have this nice little, basic but graph showing how much of compute and cooling it's saying is like 60%, other data, other infrastructure, 15%, electrical interconnect power, 25%. And if we switch to optical, then computing and cooling 60%, other infrastructure, optical power percentage. And basically it's saying like the moat shift. So I thought this is important too. It says for years, Nvidia's moat has been CUDA, its software ecosystem. If the bottleneck moves from compute to communication, the new competitive moat might become the fabric architecture itself. Who can build the biggest, most efficient, most flexible optical network for AI will have the massive advantage. And it says supply chain control. The ability to build these hybrid chips at scale depends on a few key players. Foundry capability like TSMC's CPO lines, advanced packaging know-how, and control over laser supply chains becomes critical geopolitical assets, shaping which nations and companies can build the next generation AI factories. And then lastly here, it has some big questions for the show because of the way I did the research on here. And just before I pull this off, I'll show you guys what it did for the infographic, which is similar, but it's definitely more of an infographic. We have our 75% that we were talking about earlier. We're going to need a 1,000 increase in connections needed for next-gen AI systems, which is impossible with copper, and a 10x higher energy costs for long-reach electrical singles versus optical ones. And this is obviously very, very simple. They didn't really do a good job here, but it's nice that it's moving and it's on the infographic. So it kind of looks a little more like space there. Not quite the city infographic, but that's okay. And then we have our solution co-packaged optics, which we sort of talk about. Now here it does in the infographic, it did a much better job of showing you, and we could talk more about this, how Nvidia, AMD, Intel, by the way, Intel has been working on this for decades. They are definitely foundry. I mean, they're one of the original silicon and photon researchers. That doesn't necessarily mean they'll come out on top. It just, they have a long history of data and research in this area. And then it brings the economic breakdown as well, because we were talking about this is the CUDA moat again, and then the questions at the bottom. So just wanted to show that that's more for the.
I am so glad you did show that, because it's a very impressive interactive application that you invited it to create, and an infographic.
Yeah, right.
It's beautiful. So it takes all of its deep research and creates not only a presentation in the infographic, which is a scrollable, but also has some moving image elements in it. But then on top of that, to actually build an application that you can interact with and with sliders and sort of gamifies the process of learning. Very impressive. And it just reminds me that for a totally different show and a different subject, we really need to stay abreast of what Google's doing with their guided learning technology.
Yeah.
Because that's being demonstrated, frankly, in the deep research
within
2.5 Pro. Wow. I'm very impressed with that part of it. I want to talk quickly about another player out there that's going beyond the co-packaged optics. The package that we're talking about is, I don't know if you've ever seen Jensen Huang get on stage and hold up his Blackwell device. It's a big thing. It's a package about this big, and it's made up of lots of different components. GPUs, yes, at the core, but lots of other elements of that stack that's built into that compute package. So when they talk about co-packaged optics, they're actually talking about photonic interfaces or interconnects between the different parts of that package. But there's another approach, which is getting closer to photonic computing, but doesn't require the big leap that you need to get to photonic computing, which is actually doing math with lasers, right? That's another game entirely. It's kind of parallel to what's happening with quantum computing, right? It's really making tremendous advances, but it's not yet ready for, putting it in your car yet. Okay. So there's a company out there called Lightmatter that's building what are called optical interposers and optical chiplets. Okay. And this is not putting the interconnects, at the inside the package or at the edge of the server rack to go over to the memory bank, which are also places where we can get acceleration using photonics. But this is actually when you're building the chip dies, you're putting an optical interface as one of the layers in those dies. So that just moves the photonic interconnect closer to the chip strata, right? So it's not just, hey, here's the connect at the edge of the chip, which is the co-packaged approach. It's actually, let's put them right in the layers of the chip itself and build that out. Now that's kind of an intermediate step towards full photonic compute, but it's a very interesting one. And that company is called Lightmatter, and it's the leader in this space.
One of the things I saw, I don't think Lightmatter is one of them, but just since you brought that up about companies that maybe we haven't heard of, curiously, AMD's strategy to build to what they call the zeta-scale, nice name there, engine, the zeta-scale engine. I always like when they come up with new names of these companies, the zeta-scale, okay. But the CEO, Dr. Lisa Su, has identified optical interconnects as a cornerstone of its long-term vision for the zeta-scale computing, a level of performance 1,000 times greater than today's exascale systems. So obviously exascale is a thing. But the reason I wanted to bring it up is that they, rather than deploying all the AI, all the necessary technology in-house over many years, AMD has employed the strategy of targeted acquisitions to rapidly build expertise. The recent acquisition of Enosemi, Enosemi, a silicon photonics startup with a proven track record, is a prime example. This move immediately scaled AMD's ability to develop and deploy its own co-packaged optic solutions. This follows a pattern of strategic purchases, including, would have no idea how to say this, Xilinx, no idea, for adaptive computing, and Pensando for networking, all aimed at creating a comprehensive hardware and software portfolio capable of challenging the leadership in the AI era. So almost like we were talking about yesterday with Meta, which is like, I don't have to have this homegrown. I can just go buy the ones I need. I mean, Google does this too, don't get me wrong. Like I could just go buy what I need and bring it in-house and hopefully ramp. Now, I think there's some challenges there. Obviously, it's not obviously as easy as going and buying these best in class, startups or whatever, because they all have to operate and work together. And of course, that can be very, very complex. So just to say, oh, AMD has a competitive advantage because they're willing to go out and buy startups and do this does not mean all those. I mean, hell, we can't get marketing and sales to talk to each other in most companies. So the idea that all these new companies are all going to just seamlessly start interacting and connecting, I mean, that in itself could be the downside of any company, is actually trying to do too many, M&As. So we'll have to see how good AMD is at not only bringing in expertise, but how quickly that expertise can actually make impacts across the broader AMD landscape. And that's the tricky part to me. It's not like, yeah, you have money, you can go buy a solution off the rack. That doesn't mean you can use it immediately. In fact, in some cases it makes it worse,
Right. And the sort of context in which chip design, like the history of chip design, is like Moore's law. Now that was based on old-fashioned the old-fashioned energy transfer, right? And Moore's law was that basically the number of transistors on an integrated circuit doubles approximately every 2 years. So that time frame isn't going to hold true as we're starting in this. Moore's law didn't happen until the first the first Moore was successful, I guess. I don't know. But the system in which these advances are moving forward already has that history in it, right? That we expect chip design to improve. So once the key elements of this start to have some track record, I expect we're going to see that things are able to move much quicker. And again, in the context of whether chip design can move quicker, or energy suppliers, or ways that energy is captured or created. I mean, like there is no corresponding, your nuclear power design like doubles right? You get double the amount of power every 2 years of, like, that's just not how those systems work. And just to name drop the other guy who's influential in this is Jevons paradox, right? Because as we are reducing all of the cost and the energy and all of those things, demand is going up.
Sure.
So we may still see bottlenecks, but they will be much different than the bottlenecks that we were expecting to see without these kinds of innovations.
And I would imagine if you're building, if you're OpenAI, if you're, any of them, any of the major players in your Meta, and you're building data centers, I would imagine you're building with the thought process of, can we convert this data center when the time is right to co-optics, right? And I don't know what that infrastructure looks like, by the way. I don't know how hard that is. Is it literally ripping out every chip and replacing it with the equivalent of the new silicon and photon, and it's the more co-optics version. I don't know enough about the infrastructure of how you would actually build a data center to say whether that's right or wrong. Obviously, it doesn't sound easy. We're talking about thousands upon thousands of different chips and stuff. So how easily could you convert a future data center? I don't know. But I also know if I was building a data center today and knowing that this is coming, I'm definitely building a data center that's going to make it as easy as possible for this future conversion. I mean, you would have to, right? I mean, it would be silly not to, because you could see where the future state of this is going to be.
Well, we've had those conversations before where the idea, like when, Elon went out and bought a cajillion H100, blah, blah,
Right.
blah, 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 right? And the idea that unlike other people buying equipment, it's unlikely that the data center, when the next like state of the art thing comes out, that the data center um, uh, keeps its old stuff, because not only is it less powerful, but it's also still an energy hog, right? So when you have a system that can do more with less energy faster, you are likely to rip out everything about it and create something new. And right now, that seems to be like it's just a whole new Lego, right? You just add the new Lego in the thing. But while all of this is happening, there's also research on building bigger clusters, right? So, and it's all about this, right? How do you pull clusters together that don't hit the wall of the amount of energy that can like be that can all play together in one thing without melting everything, right? So, and so there's advances happening in that too. But like it would be great if there was some add-on thing, right? Like, ooh,
Right.
put this little light thing on top of all of your non-light things,
Right.
and
Right.
now
Yeah.
everything's good.
It'll
That's
work.
unlikely.
Well, that's really how photonics made it into data centers today, because
Mm,
Intel is the company that has been building silicon photonics
Mhm.
transceivers. That's just a module that translates whatever the electronic data flow is coming through the copper wire into light to be delivered to the next transceiver. So they sell you two transceivers to kind of be an interconnect between full length racks. Okay, so here's a full rack of GPUs running, GPU servers. And now I want to get it over to this other rack to do the next stage of whatever the compute and translation into text output is, right? So that it has to actually eventually feed the application and do that over the internet. And that's going to all be electronic. That's not photonic yet. So Intel's already there in the data center.
Mhm.
They're deployed with a massive number of these silicon photonic transceivers just to transport data in between two different points with
mhm.
a little bit more efficiency. And you can harken back to the earlier part of our conversation today, where that photonic implementation is moving back farther and farther into the guts of the data center, all the way
Mhm.
to the package for co-packaged optics, and eventually into silicon photonics goes away, and instead it's all photonic compute, right? No silicon involved at all. It's a photonic compute device, and that will shrink down and also reduce the energy consumption for compute centers. So at that point, we're talking about another flurry of investment that will replace all of the billions, trillions of dollars that are being invested in data centers today with a
Yeah.
whole new technology that's better efficiency and faster compute, because it's literally, an order of magnitude faster to use photons than it is electrons.
Which is why the CUDA section in Brian's presentation
Mhm.
is so relevant, because that has been the backbone or the moat of
Mhm.
Nvidia, right? And when the next thing happens, if it's not discovered, created, whatever, by bought by Nvidia, that uh, that opens up a, a reshuffling of who the power players are. Or perhaps the power players are it's not like one bottleneck. Maybe it's something that more than one can do at the same time.
You know, look, it's going to be interesting too to see how these companies continue to get investment and stuff, because they have to be, you know, the major AI players right now, they have to be great today. Google needs to be great today with Gemini to stay competitive, right? And well, we're demonstrating one way that I think they actually are superior in one way. Not to take anything away from deep research from other tools. I just like this one, but think about that. You're in a company, you're raising funds, you know, maybe you're getting additional funding or whatever, and you're coming to people and saying, we need this amount of money because we need to build these data centers under what we already know is a ending technology. We already know what the future is, but it doesn't matter. We still need $17 billion to build these next 4, you know, data centers, because that's what it's going to require. And here's what the energy your needs are going to be. So like, we're trying to figure that out too. And it's crazy to think that these companies are probably looking at this, if all of what you guys are saying is true, is that, you know, this is 2025, by 2035, that this would all be ripped out and replaced, maybe not once, but twice. Like, things are moving at such an exceptional speed. And I think that's why I get so excited, you know, when it really comes down to, you know, the report kind of went into this too. I'll see if I can find it. Yeah, it was basically gave 3 examples, and I alluded to these earlier. Digital biology and the new age of medicine, right? We talked about what could this new technology do for us if we truly reduced energy and latency and we were moving at the speed of light. What does that actually do? What are the action items that come out of that? And I mentioned 2 of them, right? The digital biology and what it could do to do design, make, test, analyze in that area. The digital twin of planet Earth. You can imagine what it would take to process all the data of all the things going on Earth, from, you know, atmosphere to oceans, the land, ice movement, in a single interconnected way, whole. That is a bonkers thing to try to even wrap your head around, but it's going to be possible with this new technology, and that's really exciting. And the third one was the all-seeing eye, real-time AI. And it says many of the most futuristic AI applications depend on the ability to process and analyze vast streams of video data in real time with virtually 0 delay. This is true for fully autonomous vehicles that must instantly identify and react to obstacles, smart cities that monitor traffic and public safety, and advanced medical diagnostic tools that analyze live imaging feeds. Current hardware struggles to keep up with these demands, bottlenecked by time it takes to move data from sensors to processors and between processing units. Photonic processors, our interconnects, often offer a solution. By performing the key mathematical operations in neural network, such as a matrix vector multiplications, directly with light on a chip itself, these systems can achieve computational speeds measured in the sub-nanosecond range. This enables the kind of instantaneous, real-time decision-making that is simply not possible with today's electronic hardware. Companies like Nvidia are already building this capability into their roadmaps, with future accelerators in the Rubin CPX, including dedicated hardware for high-speed video encoding and decoding. So, and then it goes into the beyond tomorrow, which it calls the neuromorphic computing. That's just a cool name. Researchers are actively developing photonic neural networks designed to mimic the structure and function of the human brain. These systems use light to create artificial neurons and synapses, promising ultra-fast and incredibly energy-efficient processors that think in a fundamentally different way from today's computers. And then it goes on to talk about quantum computing as well. So really, really like important, amazing things going on right now. And while it's not directly what can I do with AI, it really is what will we be able to do with AI? How far can we push AI? We've said we can only push it so far. We're limited by a traffic jam right now. So we can only literally go so far. So until we come around with these new solutions and we deploy these into net new data centers that are, you know, on the co-optics, that's going to be the solution of getting more out of what we already have. And of course, we'll continue to move in the areas of energy efficiency and things like nuclear, but also in all other different ways. So all of that together, plus everything that's going on the AI side for just simply making the models themselves more efficient, you have a lot of things converging together to show a near future, certainly in the next decade, but maybe in half decade, where the ability of what AI can do, how it can compute, and the problems it can solve will be exponentially better than where we are sitting today towards the end of 2025. And I always say, I think that's where Alzheimer's gets solved. I think that's where cancer gets solved. I think that's where a lot of things that were just never going to be possible will be solved in our lifetime. It's going to be amazing.
And the piece of this also impacts, like, is AI has AI peaked? It's never going to get better than it already is. It doesn't need to.
Right.
Right? We keep saying it doesn't need to for all kinds of reasons. There's lots you can do with what's available now, and that can upend how things happen all over the place. But even if the level of AI was we'd hit a wall and it's stable, we haven't, it's not. But even if that didn't improve, if you improve the speed at which it can do things, if you improve the amount of context window, the amount of memory power that needs to be used in order to have a larger context window, you're doing so many things to improve what is possible without having a better AI, a more capable AI.
100% agree. And then take into what Ethan Mollick always talks about, like, even if AI didn't go any further just in that area, we haven't thought of all the ways that AI can solve problems today.
Right.
We simply, collectively, humans have not come up with all the ways that it can do. So give us 5 more years of the AI not even moving. Just give us ChatGPT for the next 5. And his argument is we'll still find net new ways to do it that are novel and new. I mean, I read stuff by him all the time. I go, how did he even think to do that? That's a novel, new. My brain wasn't even going there. We talk about this stuff on the show. So put all that together and you have a future here that's extremely promising. It's not without its challenges. It's not without potential energy problems going forward, where we simply just cannot produce enough net new energy to solve the problems we have today before we get to the problems, solutions of tomorrow. And that will be interesting over the next couple of years. I mean, we don't have unlimited energy right now, so we'll have to figure that out. But this all is going in the right direction. So with that, I'll wrap it up. I think look, guys, I told you guys before we went live, I looked at the topic today as we always do and prepare and stuff like that. I thought, geez, I don't know where to go with this or whatever. Or maybe this is 15 minutes of a conversation. That might've been. And then I did this research and I thought, oh, I just didn't get it. And so then it made me excited about trying to then relay that with you guys and what you guys said too. So hopefully if you listen to this show, you're excited. We're not there yet, but you're excited about the potential of where this can go, because we've got some super brilliant minds out there, and they're trying to solve this problem. And in fact, like people like Intel are already solving part of the problem. Tomorrow we'll have the news as we always do on Wednesday. So come back tomorrow to learn all about all the latest things. Thursday, we don't actually have a show set up yet, but I do have an idea for one.
We do have a show set up because Carl has already agreed. Thursday is Claude Code. Carl's going to walk us through what's happening. It just hasn't been put in the Slack yet.
Okay.
Sorry.
Thursday will be Claude Code.
He's going to demo Claude Code live, so don't miss it.
Yeah, no, I can't wait for that. Well, in that vein, but we'll see if it happens Friday, if we maybe push to the next week. We'll talk about it tomorrow in the news. Lovable just came out with some new upgrades, and I really want to go play with Lovable, and that's what I was going to suggest for Thursday, but Claude Code's better because Carl's already built in there. I want to go play with it because the whole thing with Lovable, not to get off topic, was with their cloud infrastructure, you had to go put your information like a Superbase or a PyCone and deal with it. And they essentially said, hey, you don't need to do that. And they actually have a really cool commercial. We'll show it tomorrow with a 10-year-old. And it ends with the 10-year-old turns to the guy from Lovable and he goes, I guess I'm an engineer. And the guy goes, yeah, I guess so. I just thought it's just a cool line from the 10-year-old. Like, I guess I'm an engineer. So I thought that was a very cool commercial. We'll talk about that more tomorrow. So news tomorrow, Claude Code on Thursday. probably our what's on our mind squirrel show on Friday, as we've been doing. Maybe we'll push Lovable next week, but we'll let you guys know. The only way to find out is to keep coming back and hanging out with us. Thank you to everybody in the comments, Greg, Jude, and everybody else. Delma, I see you in there. And don't forget, this weekend we will have our newsletter that goes out on Sunday. You can sign up for that by going to the website, thedailyishow.com. If you want to join our community, which is where I will share the report that I did, because we had some requests for that. I will share that in the community. The only way you're going to be able to get that is by joining the community. It's free. You can go to thedailyishowcommunity.com to join that free Slack community. So that's all the things we have going on. Come back, hang out with us. Sounds like it's going to be a great week. Until tomorrow. Bye, everybody.
Aloha.